Good afternoon, everyone. My name is Raskar, and I work here at AI/ML team, mostly on evaluation of various AI testbeds that we have here at ALCF. So today I'll be giving all of you like a brief overview about what all AI testbeds we have here, how you can access them, and how you can run some basic machine learning as well as HPC codes on these machines. So I'll just start with some motivation and overview of all the AI testbeds, and then the rest of the day we will go onto the hands-on section for each of the testbed. So talking about the motivation, so why do we need AI testbeds or AI accelerators? Like we already have had supercomputers using lots of CPUs, and now in last 10-15 years using GPUs. So if you see in this chart, like the performance is increasing each year with various optimization techniques. Like we moved from CISC to RISC to now GPUs, etc. But the performance is kind of a bottlenecking there. So especially with the advent of machine learning, we need more and more performance. And in order to get that extra performance, we have to move from these CPUs and traditional von-Neumann-based architectures to some accelerators that could even take this graph even further. So that's the main motivation there. So some other motivating points that I found in this paper, like in order to improve the performance, you also need to write better and better software and algorithms. So that's one of the way to get more and more performance with the existing hardware there. The other way there is, in addition to writing better software and algorithms, is coming with hardware architectures. So creating specialized hardware architectures that are just better at doing one computational task, for example, gem operations. So with this motivation in mind, like recently there's been rise of a lot of AI accelerator startups. So what ALCF has is like they have purchased like small scale systems from various vendors in the field. So we have machines from Cerebras and SambaNova, Graphcore, Intel Habana, and Groq. Like these are small scale systems, but the point behind purchasing and trying out these systems was to see if these systems could be the part of the next supercomputer. Could they be part of the next infrastructure, leader class compute machine? And if they can be, then can the current science application take advantage of them? And what are the challenges? What kind of a performance? So these are the high level questions that we are trying to address through this AI testbed systems. So getting into the particulars, like I said, it's a small scale system. So from Cerebras, we have two of the CS2 nodes. Each of the node has 850,000 cores. Same with the SambaNova, we have 8 nodes. With Graphcore, we have about 64 machine, and with Groq, we have 8 nodes. Okay. And from Habana, we have 2 nodes with each 8 nodes. So this is like high level, like how many nodes are there and what's the scale of the systems. Now throughout this presentation, we'll go inside like what the architecture of these systems mean. But for now, like this is the high level, like that's the scope of the systems. So before going into the details, like I like to present this high level abstract view about how the traditional CPUs or GPU systems, which I call like traditional von Neumann based systems are, and how all these various AI accelerators are fundamentally different than each other. So one of the main difference between those two are like with a CPU or a GPU, you have one or bunch of cores, and those cores are separated from some kind of a global memory in GPUs as well as in CPUs. For each instruction, a program counter goes through each instruction, fetches the data from the memory, and then executes it onto the cores, and then puts the results back into the main memory. So that's a typical execution flow in typical von Neumann machine. You must have heard about concepts like memory wall, and all the optimizations are basically about how you can reuse the data, etc. When it comes to von Neumann machines. With this special architectures, if I have to abstract away all the architectures, then all these cores, like memory and compute, is not separated between them. Each core has some limited amount of um, a local memory that that core can access, and all these cores are connected with very fast interconnect, and that allows them to get that extra performance that you'll see in other slides. So that's the main difference. So then how does a program graph is represented here? So traditionally, like you write your sequential program, you have a C or Python code, and your program counter is executing each instruction there. So you have to think a little differently when it comes to these AI accelerators or these special architectures. So your program is typically like before program, your architecture is something like this. You have lots of processing elements, and these processing elements are typically connected with very fast interconnect. And the yellow part there is like a memory which is distributed across all the processing elements. And then your program is represented in terms of tasks. So you might be aware of like a OpenMP tasking. So whatever program example you have to divide it down into tasks, and then you have to describe what is the dependency between these tasks, and then basically you have to map these tasks onto various processing elements onto the architecture. So that's basically how you can completely utilize these special architectures. Now, you don't have to manually do this when it comes to like machine learning stack. The compilers are taking care of all these things, but I just wanted to give you what's going on underneath there, what exactly compilers are doing. And like, because at some point, like you have limited number of transistors that you can put on a chip, so you'll not be able to have huge amount of memory onto the chip. So you have to put some memory off the chip as well. So some of these architectures that we'll talk in the next slides will have access to some kind of a off-chip memory, which could be like a HBM or DDR kind of a memory. So that's also represented in this figure. And then you have to scale out your problems. So instead of one of this chip, you can have multiple chips like this, and then they are typically connected with some kind of a interconnect. And then again, your program graph is mapped onto these different tiles through the interconnect. So that part is not much change from the one-to-one machines. So again, like I have this summary slide. I will not go into all the details of this slide, but here I have compared all various AI accelerators that we have here with one of the state-of-the-art GPUs from NVIDIA, and try to compare them with respect to how many cores, how many compute units each of them have, how much memory, on-chip memory it has, which process it was used to manufacture that chip, what is the total size of the system, what is the estimated performance that is specified by the vendors, like claimed by the vendors, what's that max performance in flops. Then this row is constantly evolving, but what kind of a software stack is supported on each of the different architectures and what kind of interconnect they use. So this is like a summary chart where it compares across all the systems, how it looks at high level. Okay, now this slide, so today for all the examples that you're going to have hands-on, etc., you are going to have access to all the 4 systems that I mentioned, and probably will have access to that till the end of the month. But going forward, if you have some science problem that you want to explore, then ALCF also has this Director's Discretionary Award, where you can, and it's quite simple request. You just have to fill out a form, tell what your problem is, why do you need access to a particular system, and you can get your hands on for the larger systems beyond the scope of this workshop. Okay, and then this slide basically just summarizes various publications we have had over the last 2 or 3 years, which have used these AI accelerators. Most of the publications are comparing the performance. For example, this LLM inference bench from previous talk, we compared performance of inference tasks across various AI accelerators, compared them with GPUs. Then GenSLM is one of the Gordon Bell finalists, where they were able to get performance on Cerebras system, and so forth. Like, just for your information, these are all the publications that we have. So before I dive into the particular details of any of the architecture, do you guys have any questions so far in the talk? Okay. So if not, then so rest of the talk or this hands-on session, basically I'll be introducing you each of the testbed, go through the architectural details of it, and then we'll switch to the hands-on session and try some simple examples on the system. Okay, so let's begin with the first one. Is the Cerebras one. So the Cerebras system is like each of these accelerator has some special quality, how they are different than others, right? So the Cerebras system, the novelty is like it's a very huge wafer scale chip compared to a traditional GPU or a CPU, which is very small in terms of area. This chip is huge. The advantage of that is like you're able to put in a lot of cores onto the same wafer. So all the memory and the interaction between the various cores, it's all happening onto the chip. So this particular chip, the second version of it that we have, it's called CS2. We have it in Argonne now, and this particular chip has 850,000 cores and 40 gigabytes of on-chip memory. So this 40 gigabytes is distributed among 850,000 cores. That comes to about 48 kilobytes per core. And yeah, it's connected with a very fast memory, as I have previously said. So going into like at another level of details. So as I said, like all the cores are like there are 850,000 cores like this, and each of this core is connected with other one with a very fast fabric router. Inside each of the core, there is a processor, there is some memory, and like this fabric router basically takes care of bringing the data in and sending it out. And that's how all these cores are connected with each other. Now this Cerebras architecture uses something called as data flow programming. So one of the main difference between the traditional von Neumann versus data flow is in von Neumann, as I explained earlier, program counter is deciding which instruction should be executed. In data flow programming, tasks are activated or triggered when the data packets arrive to that chip. So the instructions are already there, and let's say you want to do C is equal to A plus B on this particular chip, then when the data that A and B arrive to that chip, then only that particular core gets activated and it executes that code. So that's one of the main fundamental difference. Now speaking about at a practical level, you have these huge large language models or machine learning models, and there is only 40 gigabytes of space on chip on this chip. So in order to enable like practical models, they have these memory X and SOM X systems, which basically make like the weights of the models or the data is basically streaming in and out of the system through the system. So in addition to the main chip, we also have these other nodes into the system, which take care of bringing data into the system and getting the data out, and taking care of compilation and mapping the problem onto the chip, etc. So with that chip and view, so what exactly we have here at ALCF, the cluster consists of the two main chips, a management node, 16 worker nodes, and certain like 24 memory X nodes and SOM X nodes. So all of these come together work to execute your program. Now you don't have to worry about all these details like as a user, but because all of these details are kind of abstracted away when you're actually running the code, but it's better to have idea about these things. Okay, then next I'll talk about software stack. And in particularly I'll talk about PyTorch. So PyTorch is supported, it's a different spin of PyTorch. So there are some Cerebras specific functions there which you have to use, but this is how a particular like you can take a model that you have in a PyTorch, and then you can use Cerebras's scripts, etc., and get that model executed onto the chip. And And how exactly all of this happens, I'll explain in the hands-on section. Like we can go through the code and we can see like what it exactly means. So yeah, again, like they call it CS Torch software stack, and there are a lot of details like which compiler toolchain it uses and how everything works, like how the PyTorch code is lowered down to the actual chip, etc. But again, like this is just for information. You don't have to worry about this when actually running the code. So yeah, that's like pretty much high level overview of Cerebras system that you need to know as a user. Now we can jump to the okay, not to the mail. Okay. So now we can jump to the hands-on section. So I'm pretty sure you guys have access to this repository. So in this repository, you have to look for a folder for AI Testbeds, and this is the directory we'll be using for our hands-on session. So in particularly for Cerebras, I have created a directory for Cerebras. So that's the one you have to use. So yeah. So in addition to this GitHub repository, another useful resource is ALCF's documentation page. So it's docs.alcf.nl.gov. In here, you have to look for AI testbeds, getting started. So this is a good resource to get started on these systems, and there are pages for each of the system here. So I would have these two tabs open on your system to debug any issues. So to give again like practical idea about how to access these machines. So to access Cerebras machine, so you have to go to your terminal on your laptop and SSH to cerebras.alcf.nl.gov, and that will get you to one of these login machines. So all of you here should already have access to this, and the password that you have to enter is similar to what you do for Polaris or Sophia, which is from your mobile pass. So does everyone have access here or is able to connect to the system? Is anyone interested in following along? So now is a good time to do that. So yeah, I can follow this step along with you in my terminal. Okay. I think that's big enough. Yeah, so simply SSH with your username to cerebras.ai, and that should ask your mobile password. Yeah, and the load balancer will automatically put you on one of the login nodes, and it's put me on login 01. So yeah, that's how you connect to the system. So yeah, please feel free to stop me if you have any questions. I can zoom into this. Yes, it's a different, yeah. You have to use the same password generating app, but you have to SSH to something else. Yeah. Now there are multiple users like us that are trying to use this system. So it has a job queuing and submission system, which is something that Cerebras has provided to us. So you can learn more about that system here, like under Cerebras job queuing and submissions. So this is where you will find all other commands. So csctl get jobs is the command which basically will tell you about all the jobs that are currently running. So as we can see here, someone is running, like one job is running on the system, so the other node is available. Yeah, and if you want to know what other options are there available with this job sharing, you can use this. It's pretty much similar to, or not similar, but it has some of the functionalities that Slurm has. Yeah, so that's all. So now that you're on login node, now we can dive into the actual hands-on part. So for this workshop, I have divided the hands-on part into two sections. So one of the section is targeted for Cerebras' PyTorch software stack, which is used for all the machine learning related workloads. And the other software stack is called Cerebras SDK, which is targeted for all the HPC applications. So we'll begin this hands-on session with the PyTorch one because, yeah, so for your reference, I'm in AI Testbed, Cerebras, and PyTorch. So similar to GPUs, like you have to, like currently you're still on the host machine, right? You're still on a CPU. You're not exactly running your code on the chip. So you need to give all the software libraries that are typical. So the first step once you get on the login node is to create a virtual environment for running any applications. So these are the steps to create that virtual environment. Basically, you're just creating a new directory, deactivating any existingly activated virtual environment in Python, remove any directory if you already have created that. And then we'll be using this Python 3.8 distribution that's already available on the host node. And you'll be using that to create a new virtual environment called as VN. Like you can give any name here, but here I'll be giving this name to it. And then you'll simply be activating that. And then you'll be updating the pip that's installed there and installing this Cerebras PyTorch 2.3.0 version there. So that's how you get access to PyTorch on Cerebras. So yes, right now you're on login node onto the getting started here, right? So this is all on a host. You're on a CPU. Nothing to do with the chip here. Yeah, so I believe I already have this virtual environment. So I'll start with this. Yeah, so while that's going on, feel free to like stop me anytime in between if you have any questions during the hands-on session. Other than that, excellent source is the Slack channel. So on our Slack channel, like there is a Slack for track 2 as well as for AI Testbed. So feel free to post any errors that you're getting or any questions that you have there. Me and my colleagues will be monitoring that and we'll try to help you on the Slack itself, or I can also try to help you. Okay, so now that it's done, so I'll be creating a new directory called as R2.3. That's just a version of the software that Cerebras has. So once I'm inside, I'll be basically creating a new virtual environment here. So this will take some time. Okay, and now it's created, so I'll be basically going inside that directory and activating the virtual environment. The next step is to upgrade the pip. And then install the Cerebras PyTorch. Yeah, this is only one-time process. Ideally, you should do this for each application to keep the software dependencies separate. Okay, so while that's going on, so the next step is Cerebras Model Zoo. So Cerebras on GitHub have this repository called as Cerebras Model Zoo. So Model Zoo is nothing but like various models and applications, etc., that they have ported to the Cerebras. So we'll be using one of the examples from this model zoo. It has various examples. You can go into the models and you can check various models from, these are all NLP based models like Bloom and Llama, Mixtral, that you have heard about. So today we'll be trying out this Llama model in there, but yeah, you can try other models as well in your spare time. So the instructions for that are available here. Like if you go to docs page for ALCF, there are various step-by-step instructions for various models, including Llama 7B. But in addition to that, there are also instructions about how to get BERT running or GPT running. But today we'll be following instructions for this Llama 7B model, and we'll be training this. Okay, so we are still setting up Cerebras PyTorch here. Okay. Okay, so it's done. Okay, so I'm already inside this already inside this directory. So now basically I'm going to clone this model zoo here, which yeah, and inside the model zoo we have to check out the correct version because the PyTorch version that we are using is 2.3.0 for Cerebras. So we just have to use the correct release here, which is 2.3.0, in order to not get any dependency issues. So you just have to check out that particular release. Okay, so we have everything in order here. So yeah, I will. So I'll open this directory in VS Code for our reference. Somehow it's not working. Okay. Yes, all of this is on login node. So far we have not done anything on the chip. Okay, so VS Code is giving me some issues. Typically it doesn't happen. Okay, but we can continue. So we are so the next steps are to activate the PyTorch environment. So that is already activated in our case. But the next step to that is we have to install all its requirements. No, it's something wrong with my system. Yeah, so there is a requirements.txt file here, and it has all the requirements that we are going to require to get that particular example running. So we'll be just installing this with this pip install, yeah, with this command. Okay, so while that's going on, let's look at the next steps. So that's pretty much all like you have to do, and with that, you're good to run uh, all the examples inside the model zoo. So for this hands-on session, I'll be walking you through a step-by-step directions to get Llama 2 7B training working on Cerebras. If you're looking for a simpler example, there is also example for running MNIST here in the repository itself, as well as there is instructions to run BERT here. So I'll not be going through that right now for the sake of time, but in your free time, feel free to do that. Another resource I want to point you to is this datasets path on Cerebras system under /software Cerebras. Like commonly required datasets are all available there, so you don't have to re-download them. Okay. Okay, so while the requirements are being installed, we can move on to the next instructions to actually running the Llama training code here. Yeah, so while that's going on, maybe I can start another terminal and connect to CS2. There is no. Okay, so let's take a look at some of the files that are part of this. So model zoo, NLP, and Llama. Okay, so this is what exactly we are going to run here. So now this is the part where we are actually going to run something on the chip. So as I have said earlier, like most of these parts are already abstracted for you. So you will not see like all of this is part of the Python script. So what exactly you will be providing to the model are like these config files. So in particular, this parameters llama 2 config file. So in here you have to give like point to the scripts, like where exactly you will find data for your input, where is your input data, which data it should be used for validation, etc. So this is the file that you have to actually edit in order to get the model running. Because this file is provided by Cerebras, these data paths and other parameters don't exist on ALCF systems. So we have created this config file which will actually work. So for your convenience, you can just copy this file from this location, which is under datasets, overwrite it with the current config file, and you should be able to use like all the data sets, etc., which are there. So while the require, yeah, it's done. So now you simply have to go to the correct directory. So that was source, Cerebras, model zoo, models. That'll be okay. So this is where we are. So there is a config.py here. So there is a inside configs. There is this file for llama 27b. So this is the file that we are going to replace. So the file that we're going to replace it with is this. So that file basically, as I said, like looks like this. So it's actually pointing you to the correct data directory for the data set. So everything is kind of converted, the data set is converted into correct format, etc. And it's ready-made for this demo here. So those are the only parameters that are changed in this config file. And other than that, yeah, like this part, like maximum number of steps here are 300 instead of the original that model training requires. This is mostly done to speed up the training for the demo purpose. So yeah, this is the config that we are going to replace it with. So we'll take this and replace it with params llama 7b in this file. So yeah, it will basically overwrite it. Now in this part, so this run.py is the script that we are going to run, and it's going to take care of everything like the job scheduler and everything. So what's happening here in this command line is the first parameter you're giving it is CSX. So this basically means you're running this code on a Cerebras system or on a CPU. So this is what is deciding that. Then you're giving some job label to this job, which is llama 7b in this case. Then you're pointing it to the correct parameters file. You're specifying how many number of Cerebras systems you want to use here. We're just going to say one. The mode, whether training or evaluation. Then the model directory where the like the model, whatever the intermediate results and scratchpad is stored. What all directories you want to mount for this and where they should get mounted, that location, and the Python path for the correct virtual environment Python that you want to use, and the compilation directory. So these are all the parameters that you have to give, and this will automatically compile as well as run the job for you. So first we are going to get out of configs. Yeah, and we are going to export our model directory as a directory in this current directory. If this is just a safe keep, if that already exists, then you're going to remove that. In our case, it was not there, and then you're going to simply run this on one CSX. Okay. Did something wrong. Some extra white space or something. So maybe I'll copy. This is the command. Okay, I see a lot of people already queued there, so probably that's why. Okay, so that's how you run a simple example. Uh, and once my job is queued, the expected output will look something like this. Like it will output all the information there, and it will continue the training for number of steps that you have provided, and that's pretty much it. So any questions so far? Any issues? Are you guys able to run this? Okay. Okay, so while I'm queued waiting for resources, we can move on to the next part of the hands-on. Um, so the next part I want to cover is like, this is how you run like your ML applications, but how would you do it if you have like some HPC kernel? So for that, Cerebras has this different software stack. It's called Cerebras SDK. So basically, you use a language called as CSL to program whatever example that you have, and then it has some Python wrappers to write a host code. So it's similar to like a CUDA programming model, like a host and accelerator kind of a programming model. And using these tools, you get your program to run on to the underlying uh, machine. So this Cerebras SDK has two parts to it. One is you can run this code in a simulator if you don't have access to actual CS2s. Once you perfect your code, then you can actually run it onto the CS2. So this is like a high-level software stack for Cerebras SDK. So as I was explaining, from programmer's perspective, you're writing your host program in Python. This code takes care of like creating all the data onto the host and then copying it to the actual device, which is CS2 in this case. Those programs, accelerator programs, are written in CSL. They execute the programs in data flow fashion and then send the result back to you. So that's a high-level programming model. CSL language it itself is a big topic, so I'll just cover like high-level thing. So it looks very similar to Zig. It looks very similar to C if you're aware of that. It has all the functionalities that a typical programming language has, like types and functions and control structures, uh, conditionals and while loops. And obviously, like the format is a little bit different, but you can get everything done. It has different data types, etc. Again, I'll not get into the details of all these, but if you spend some time learning about it, you can get familiar with it. Then it also has some features like comp time and creating parameters, which are like command like arguments and modules, which allow you to, like it helps you with the programmability. In addition to that, it has some performance features like creating tasks that I was explaining earlier, like you can create various tasks and dependencies between the tasks. So all of that data flow kind of programming model you can create with this programming language. Now to give more motivation about this, so there are various papers published which are using this Cerebras SDK to get like massive, like about 150 to 200 times speed up over like traditional GPUs. So these are various papers. You can go and read about how exactly they did it. Those repositories are available. You can try that code onto the system. So all of that is possible. Now let's get our hands on to this. So yeah, so this section is here under Cerebras. There is a directory for SDK. So this is where you will find instructions to run your examples. For this hands-on, like we'll be using GemV example where we are going to multiply like a matrix with a vector, and then that's our output. And as I explained earlier, there are two ways to do this. One is using the simulator, and other one is appliance mode, which basically means you're going to use the actual chip to do this. Now for simulator, basically the simulator works using a singularity container. For this demo, I'll be showing how to do this on the Cerebras login node that you already have access to. So all these dependencies are already installed there, like singularity and other dependencies. In order to use this simulator onto the system, you simply have to, like we have provided all the files required for it under software Cerebras CS SDK. So you just have to copy those files from there to your home directory. Just add the path to this copied directory to your path, export it, and then you're ready to start using the simulator. Yeah, so other than that, if you don't want to use the simulator, you have perfected your code and you want to use the actual hardware, then for that you require some additional steps, and those steps are also mentioned here. Another note about this simulator here is like yes, you can run it on the Cerebras system at Argonne, or if you have a laptop that supports Singularity, then you can run simulator there. Or if you want to get it running on Apple Silicon Mac, like what I have, that's also possible, but you have to take some additional steps there. And the instructions are available all on the Cerebras documentation page. So yeah, you can follow those instructions for Apple Mac as well. Okay, so with that we can get started with this. So the first thing, as mentioned here, you just have to copy this particular directory to your folder. Let me one more time try this. Okay, looks like it's not going to work for us. Oh yeah, so my training job is scheduled here, and we can see some progress here. And using this, you can see like my job is running. So yeah, anyways, like so the first step was to copy that Cerebras SDK to your home directory. So I have already done that, so I would just show that SDK to you. So SDK consists of various parts here. So the main one is this CSLC, which is the compiler, and they have a version of Python, so you have to use CS Python to execute your host code. So those are the main things you need. Other than that, you also have this SDK debug shell, which is used for debugging or like making sure everything is running fine. Then they also have this CSL extras. This basically consists of examples. They have lots of tutorials and benchmarks. So you can follow these tutorials to learn about the language, various features that it has. Or they also have these benchmarks like GEMVs and FFTs and stencil operations, etc. So Cholesky, so you can also directly run them or go through that code to see how various optimizations work. If you are VS Code user like me, then you can also use these extensions for syntax highlighting for Vim or VS Code. So all that is present in that software package. So the one that we are most important one is again this compiler. So you basically have to add this to your path, and you should be able to compile the programs. So we'll start with this first hands-on example, which is for GEMV simulator. So I have copied this example from this repository. So another thing that I want to point out to, like Cerebras has this GitHub repository for CSL examples, which consists of all the benchmarks and tutorials that I just showed you. So for this example, like I'll be just walking you through this GEMV example that they have here. So going back to our repository, in order to run this GEMV example, there are several parts here. So the first part here is this run.py, which is our host code. So for, the host code basically consists of yeah. So for host code, first you have to uh, import SDK runtime, and then there are various functions on the host side you use. So the main parts here are like you're constructing your matrix A, X, and B. B is a bias here, so it's not exactly GemV. It's GemV plus bias. It's AX A into X plus B. And then this is where you're constructing your SDK runtime with various command line arguments that you'll take from here. And then basically you have to run this. There is runner.load and run. So this is similar to like CUDA execution calls. Like this is exactly where you're initiating the kernel, and you're calling like init and compute function, which is on the accelerator side. Okay, so what else is important in this code? So yeah, this is where you're initializing your data. This is where all this part is where you're, this is all like scratchpad code that you have to use in order to set up that host accelerator programming model. And this is where you're copying your data from device to host. So they have these functions for device to host copy. So yeah, make it bigger, yeah. So this is where the you're copying your A and X to the accelerator, and then once it's done copying, you're going to stop your runner, and this is where you are just asserting that your results are correct. So this is how like a host code looks like. It's a simple Python code. On the accelerator side, you first have something called as a P program. So in a P program, you're again creating space to get those A metrics and B metrics. You're creating those memory locations there. This is basically you're defining size of your metrics. Yeah. And then the init and compute function that we called from the host side, that's present here. So this function is first basically initializing all like matrix A and B here, and then calling a GemV function. So they are here, like initializing is basically you're initializing using the CSL, you're initializing your matrix and vector, and then you're basically calling GemV here, which is yeah, this is the part which is the GemV kernel here written in CSL. So it's very similar to how you write like a C code, like there are two for loops and you're going through each row of a matrix A and multiplying with a vector. So this part and then storing it in a temporary variable and then updating the final vector here. So that part is pretty much same as the any other sequential code. So this is the code that actually gets executed on the P that I have mentioned here, like this P. So on each of this P, this is the code that gets executed. Now, in order to use multiple Ps or the entire chip, there is another file which is called as layout.csl that we use. For this simple example, we are just going to use one PE. So we are out of 850,000 cores, we are just going to use one processing element. And then there are these constructs that are used to set that size, like the size of the rectangle is 1 by 1. And then you set the tile code. So the p program.csl that I showed earlier, that should run on this tile. And then the y is the output that should be sent back to the host and the name of the function to call. So these are all the, like, again, these become like a scratchpad codes for a layout.csl. So this is how this looks like. And then there is this commands.sh. So this is the normal script, bash script that you'll be using to run all of this, compile and run all of this. So this consists of, first line is CLSC. So this is the compiler. You're going to specify which architecture you want to use. So we are going to use CS2, which is wafer scale engine 2. Now, like there was also 1 and latest one is 3. Then you're going to point it to your layout.csl, then give some dimensions. This should be bigger than the 1x1 tile that you're going to use. In this case, you can just say 8x3. The fabric offset, so it's again used to where exactly to map that code, the output of the compiler, and like these are all various memcopy flags there. Like you have to copy some memory from host to device or device to host, and how many channels to use. And then once the compilation is done, you're going to call cs python to run this script. So let's do that. So you can get this example either by cloning this repository and then going inside this repository and simply running this commands.sh, or you can also get this example from CSL examples. So in my case, instead of cloning the repo, I would go inside CSL extras and examples, tutorials, and gmv01. So yeah, so here I'll just run commands.sh. Okay, because I have not done this step. Yeah, so I had not added this directory to my path. So with that, I have it. So basically this will be invoking the SIF file, which is present inside that directory here, which is this file. And it will compile the program. And once the compilation is done, it will again use the same Singularity container to compute the program on the host and accelerator, and then compare the results, and then it outputted the success. So far we are doing all of this on the login node. So this is through a simulator. There are some additional steps required to do this onto the actual system. So that's what these next instructions are about. So this part of instructions are pretty much same like the ML stack. So basically you're creating a new virtual environment and upgrading the pip. So you can use the existing environment that you have, and you just have to install a couple of more extra dependencies here, which is Cerebras appliance mode and Cerebras SDK. So that's what I'll be doing. So first I'll just activate the environment that I had, so which was R, not here, R2.30. Yeah, so I'm inside this virtual environment now. So these steps are only required to use the appliance mode. So I'll install that, and then the Cerebras SDK. Okay, so with that, you're pretty much ready to run this GemV example that you just ran on the simulator onto the actual Cerebras chip. So before getting into this, let's check what's the status of the code that we're running. So I think it's still queued. 3 compile jobs queued before my current job, so still in queue. Okay, so there are few changes that you have to do in order to run your CSL job from simulator to actual appliance. So on the run side, you have to use this SDK runtime that you just installed. So you have to use that. Other parts about creating like a space for A, B, all of those things stay the same. This part is new. So during the compilation stage here for the appliance mode, a JSON file is created. So you have to give that JSON file to this host program, and in order to get your code running onto the appliance. So those are the main changes, like not much, but there are few changes to on the host side of the code. Um, the P program stays pretty much the same, so there is no change for that. Same goes for the layout.csl. So we are still going to use one P here, so that part doesn't change either. What changes are these commands used to compile the program. So earlier we used CSLC, Cerebras compiler, to compile that, but now we'll be relying on this compile.py script that Cerebras has provided to compile this script, and then we'll be simply running Python. So our shell script changes. So how does this compile.py looks like? So here again, you'll be importing this Python package called as SDK compiler, and you'll be giving all this information like this is my layout.csl, and these are going to be my fabric dimensions, etc. So with that, you can get your code running onto the chip. So because I don't have that on here, I'm going to clone this. Then okay, so basically I just have to run this command start sh, and now it will compile the code and run on the actual hardware. So this step is looks like it's stuck, probably because I'm in the queue. So compilation for this job, it still gets queued. So if you do cstcl, if you open a new one, what was yeah, so a lot of queued jobs, and I'm also queued. So yeah, this job will get back to this job once it's executed. But those are pretty much the instructions to run your HPC code onto the architecture. So as I said earlier, like you can visit the CSL examples. There are lots of tutorials here. So this example just ran it on one PE. They have expanded here to using it on multiple PEs. Then you can use routes to communicate between various accelerators. You can use streaming mode. You can use FIFO buffers or race pointers. So there is a lot to explore there. So feel free to do that as next steps. So that's the end of the hands-on session for the Cerebras. So any questions? Yes.
Let's just say I want to run an AI model on Cerebras or any of the AI testbed. I assume that you have a version of PyTorch that's modified for a particular system.
Yes.
And when I want to run a model, I need to install all of the packages. It might not be included in the requirements.txt. So I have to install some extra packages. But those extra packages may not be compatible with the one that you want for the system. If I do a pip, it might overwrite some of the packages that's already installed. That is required for your system. And then if I install my own, if I somehow manage to install my own, it might not be compatible for your system. So, so how do you go about installing all the compatible packages to allow my AI model run on the system?
So I would say there are two parts. Like there are packages that are vendor specific. Like in this case, there is a Cerebras PyTorch. So that has a different package name itself. So you will not be replacing that with the PyTorch. Um, then the other packages that you're talking about, they typically are for the host side. They are not for the Cerebras, or they are not for the accelerator related. Maybe they are related to the NVIDIA GPU CUDA or whatever. So they will also not get, I don't think there will be that issue. But what you will have to do is you have to look for, so that's where the porting part comes in, right? Like in order to port a model to this accelerator, you have to see, see if whatever packages that work on GPUs, is there an alternative version for that on these accelerators, how to work with that, etc. But the host related packages, because even with the machine learning models, like for example weights and biases, they also work on AI accelerators, because that host and biases part is running on the CPU, not on the accelerator. So there's not that issue.
The code will run on either CPU or GPU. When it doesn't detect a GPU, it will default to CPU, right? So it should run on the system.
So yeah.
If the correct packages are installed.
Yeah, so in order to take advantage of accelerator, you have to use correct package that's provided by the vendor, and there is this particular way to access the accelerator itself. So the programming won't be same as how you access the GPU. It will be different. For example, in Cerebras's case, if you want to use the chip, you saw like you have to depend on the run.py that they provided. So you just take your model, and then there is a lot of porting efforts, and then you are able to run it on the chips. So because you don't have the correct packages, the model is still running on CPU, that will not happen. I mean, if you just take a PyTorch code and run it, then it will run on a login node, but you will immediately see that it's not using the system. Yes. So that depends on the vendor support. So NVIDIA has support for libraries to measure the power, or profiling tools where you can monitor the power, or you can simply do NVIDIA SMI and see how much power it's consuming. So such a tools do exist for some of the accelerators, but not all of them. As far as I know, Cerebras don't have a tool which allows you power measurement. They don't even have like a profiling tool. But if you look at other architectures, like for example, SambaNova recently have support for power measurement. Graphcore has very good profiling and power measurement tools. Same for Intel Habana, or Groq has a profiler called as Groq View. So support for profiling and getting insights, like a performance counters, etc., that varies from vendor to vendor. Yeah, and other than that, you can measure the power, for example, at a node level, etc. You can work with admins to do those kind of studies. But yeah, from vendors, support varies. Yeah. Any more questions? Okay, if not, we can move on to the next test bed. I don't see any questions here either. Okay. Okay, so the next test bed I'm going to talk about is Graphcore. So Graphcore has this chip called as IPU. This is a picture up here. It's called Intelligent Processing Unit. It has a similar architecture in abstract way, like it has bunch of cores and each core has some local memory. Going into the details of it, like I think there are around 1,472 independent IPU tiles, and total memory with one chip is 900 megabytes. Again, it's a SRAM distributed among all the cores. And then all these chips are connected using a fast interconnect. Yeah, yeah. And all these chips are connected with each other with a fast interconnect. It's called IPU links. To give analogy, it's similar to something like NVLinks that you are aware of in NVIDIA GPUs. So this is like direct chip-to-chip interconnect. So this is a slide where it compares like CPU to GPU to IPUs. So as mentioned earlier, like the main difference is like huge amount of cores, and each core has some local memory, and the programming model is different. It's called MIMD in their case. GPUs are SIMT, so single thread, single instruction, multiple threads to MIMD. So that's the main difference. Then looking into the software stack, Graphcore has support for vast number of machine learning applications, from GNNs to large language models to CNNs. Then primarily they do support TensorFlow and PyTorch, but today we'll be only focusing on PyTorch, and they have support for all these frameworks. For their HPC software stack, they have support for this Poplar and Poplibs, which are like libraries built on top of Poplar. And then they have support for all these profiling tools like Graph Analyzer and System Analyzer. So that's like overall how the software stack for the Graphcore looks like. Now, one of the main difference between the Cerebras architecture and Graphcore and others is Graphcore uses something called as bulk synchronous parallel model. So Cerebras used like data flow. So each tile or each core was executing the instructions only when the data came to that core. So what Graphcore does is different. So there are these stages onto the Graphcore chip. One is sync, one is compute, exchange, and waiting. So all of the cores, all 1,472 cores are either in either of these states. So either they are doing a compute, and once compute of all the cores is done, then they will exchange the data that they have computed, and then they will again go into the compute. So the processing happens in these lock steps. So BSP model is from 80s and 90s, during when supercomputers were mostly from CPUs, and they were trying BSP is one of the models that was famous at that time, and there are lots of algorithms written about it. But Graphcore was the first company to put that BSP model onto the chip from the entire supercomputer. So that's the novelty here. So like that's all I had from slides, like a very brief idea about the chip and the software stack. So with that, we can get into the hands-on part for Graphcore. So the instructions for that again are here onto the Graphcore directory. And then similar to Cerebras, I have divided them between the PyTorch and the Poplar. So one is for machine learning, other one is to do HPC. So this is the connection diagram for Graphcore. It's a little different than the Cerebras. So from local machine, you have to get on to one of the login nodes that we have here. And once you're on login node, you have to do another step. You have to go to one of these Poplar nodes. So we have 4 of those, so you can connect to any of those. And once you're on either of those nodes, you can use some kind of a job scheduler to get access to one of the 64 IPUs that you have. So yeah, let's do this. So first step is to connect to the login node, and I'm missing something. GC. Again, you enter your password. Okay, so you're on the login node. And from here, once you're on this login node, you have to connect to one of the popular nodes. You can choose any of the nodes. Maybe I'll choose this number 3. Okay. All right, so now we are ready with the next steps. So once you're on this popular node, so similar to the model zoo that you saw in case of Cerebras, Graphcore has something called as examples directory. So let's take a look at that. So this is examples directory from Graphcore, and as I mentioned, they have examples from graph neural networks to NLP to speech. They have lots of tutorials. So this is a very good source to get examples that are already working onto the Graphcore architecture. So today we'll be using examples from this examples directory. So first thing to do there is to clone this repository. I believe I have already cloned this. Yeah, so I already have a copy of this. So I'll skip these steps, but this is simply cloning the examples directory. Now, Graphcore system supports Slurm, so all the job scheduling and monitoring tools that you are already familiar with, they can work on the Graphcore system. So like I have given some of them here, like you can do a batch submission using sbatch, or you can do srun to do like an interactive job submission. You can cancel jobs, etc. So yeah, all those tools are supported here as well. What was missing on Cerebras, which is present here, are the profiling tools. So Graphcore has rich set of profiling tools. They are divided between graph analyzer tools and system analyzer tools. They have different purposes. If you have time later today, or if you guys are interested, we can profile one of the application and see how the output looks like, how you can use these tools. But I have provided instructions here to use. For example, if you want to generate like a use like Graphcore popular graph analyzer, then you just have to prepend your execution. Like if you want to do Python mnist, then you just have to add this command before it, and it will collect all the profiling data, save it to this directory that you give here, for example, Graphcore profile, and what kind of a performance metric that you want to collect, like power or flops, etc. And then you can visualize all that. And similar instructions can be used for system analyzer. You can use both of these together, so that's not a problem. And these profiling tools work for everything in the software stack, including PyTorch and Poplar. So yeah, at high level, this is the information for Graphcore. Now we can get started with some of the machine learning examples. So here I have also provided like mnist and ResNet, which are much simpler examples. So if you want to learn about what are the exact differences in doing a simple ML application on GPUs versus Graphcore, then I would recommend you to start from here. So for today's hands-on, similar to what we did on Cerebras, we'll be running the GPT-2 retraining onto the Graphcore. And then again, like the previous accelerator, you have to create a virtual environment, install the dependencies, and then you can run your examples. So that's what we will do. So similar to Cerebras SDK, like there are different versions. So Graphcore also has popular SDK in various versions of it. It's available under /software Graphcore popular. So you can simply use this command to enable that. It should be enabled by default, but this is just to be safe. So it will probably throw an error that it's already enabled. So we are good. And then you have to create a new virtual environment. So yeah, I believe I already have this. Yeah. So let me start by removing it. Okay, so while it's getting deleted, we can switch to the example. So the next steps are to create the new virtual environment and install the wheel for pop torch. So similar to CS torch, they have something called as pop torch. So we have to install the correct wheel for that and install the correct requirements for that application. Okay, so that's done. So let's follow the instructions. So yeah, we'll create a directory and create a new virtual environment called as poptorch 3.3, and then we'll activate it. So it's activated, as you can see here, and then we'll basically install the Poplar SDK there. So we are just, for our convenience, I'm going to export this. And simply install at that particular location this particular wheel, which is again available at this /software/Graphcore location. Yeah, so with this we have PopTorch available for us. So the next step is to install the requirements. So in this case, we will be using this GPT-2 PyTorch example. So which is in examples NLP GPT-2 PyTorch. So like this is the code for this GPT-2 that Graphcore has provided us. So there are a bunch of requirements. So that's what we'll be installing next. Yeah, first we have to go there. Examples. Yeah, so we are in the correct directory, and now we just have to install this requirements.txt here. So yeah, this part is pretty much common across all the AI accelerators, like creating a virtual environment and then installing their version of PyTorch and then requirements. Okay, so once that's done, we are going to look at the instructions to run this GPT-2 example. So the example that I have given here, it uses 4 IPUs and it uses like a single instance to compile and run it from the scratch. So we'll be using srun, slom. Then we are requesting 4 IPUs for this job. And then we are simply invoking this train GPT-2.py script here. And all these are like command line options for this script. So the same script is used for various versions of GPT. So we are going to say this is for GPT-2, how many replicas you want per IPU, the replication factor, and all these various, like how much will be batch size and layers per IPU, how you want to distribute it. So this is just one of the configs there. So you can, and we are just going to run this for one epoch for the sake of time in this case. And the data set, like you can also train this model with the actual data set, but Graphcore has this way to give like a synthetic generated data set. So that's what we'll be using for this example. Yes. So mine is in queue. So the way to check that is you can go to your login node and type this cstcl get jobs, and then it will show you what all jobs are running and what is queued. So I have 2 jobs queued there. So similarly, you can see, so there are only 2 nodes, and for compilation as well as running, like there is a queue for everything. So yeah, that's the current status. Yeah. Okay, so we are done installing the requirements. So next we will run, and we have like 64 IPUs in this case, and we'll be just using 4. So hopefully we can get some resources. So yeah, that's my job ID in queue waiting for resources, and yeah, it will get executed, and because we are running it interactively, we can come back to this window to see the results. So so I'll not be running the next step. So similar to running on 4 IPUs, like I have a command here, which you can use to run it on 16 IPUs. So IPUs is equal to 16, and then for that particular configuration, like I have adjusted like number of replicas and how layers should get mapped to the IPUs, etc. So yeah, that's another command there that you can try on your own for 16 IPUs. Okay, so here also I'm waiting. Then yeah, we can see with SQ command what's our job up to. So this shows my job is running. So yeah, my job is running. So yeah, this is how the output looks like. My job is queued, then I got resources, and then it started running on 4 IPUs. This is how it distributed various layers across the IPU, and then all this output. Yeah. So yeah, that's all I had for the hands-on session for PyTorch using Graphcore. Okay, so next we can take a look at like a popular, so HPC software stack for Graphcore. So just a brief overview. So I have already showed different version of this software stack earlier, and we did take a look at this PyTorch, and similarly TensorFlow can also work. So we did take a look at ML frameworks that are supported. But what if you have like a HPC application? So for that, Graphcore has this popular software stack, and for convenience, they have all these libraries like you have for a CPUs or a GPUs, like linear algebra library or randomization library, neural network library, sparsity library, etc. So basically, we can use those libraries to port your HPC codes to the Graphcore architecture. So that's what the next session will be focusing on. So the programming model here is a little different. As I explained in the beginning of this presentation, the basic idea to use these accelerators is create these program graphs. So Graphcore has a different spin to it. So they call it computational graph. You can create different variables, which is data stored in each of that task, vertices to, they call them the compute tasks to connect, show the dependencies between various tasks. So that's like a high level programming model for Popular. Then to get into the details, the graph is made up of data, compute tasks, and edges to connect various tasks to each other. Variables could be 3D tensors, 1D tensors, 2D tensors, etc. Again, like because this architecture is targeted for ML, they have support for all these data structures which are common in machine learning. These variables then get mapped to the various cores that Graphcore has, and then they operate in this compute set. So all these various variables can be combined together for locality, etc. inside the compute graph, and they call it compute sets. And the bulk synchronous parallelism model that I showed earlier, so that basically works at a compute set level. So all the all the compute sets in a graph are either doing compute or exchange, as it's shown in this diagram. So that's like an overall programming model. Then this slide basically will again look at this slide into the hands-on section again. But this is how a host program looks like for Poplar. So you have to, it's in C, C++. So any HPC programmer should be very familiar with this. So you have to start by including this engine and the namespace. You are basically following exact steps that I just showed, like creating the graph, then adding the codelets, so various nodes to that graph. Each node has a separate CPP file for that, or all nodes can use the same CPP file. Then you're creating this graph, adding graph and various programs into it, and creating an engine and letting the engine run. So this is how a host side looks like. And codelet is what basically they call what the piece of a code that will run inside each vertex, inside each tile onto the accelerator. So that is also a C, C++ code. So you create a vertex and then you have your data there and you do the compute part. So that's how this host and accelerator programming model looks like. Yeah, and these are more slides. So we can go through this into the details into the hands-on section, how to create control in the programs, etc. So because we're running short on time. Then this slide talks about the profiling tools. So they call it Pop Vision tools. As I mentioned earlier, they have Graph Analyzer and System Analyzer. Graph Analyzer basically creates a traces like how much memory each tile is using, how is the utilization, etc. How much is the power consumption, etc. And then the system analyzer basically tells you about, it's a tracer, like how much time was spent in copying data from host to device. So all that information you can get from system analyzer. Now we can move on to the Poplar hands-on section. So similar to Cerebras, for the sake of similarity, we'll be using the same matrix vector multiplication example here. Similar to Cerebras, there are two ways to do this. One is through the simulator. They call it IPU model. So when you're running a program through this, you're only going to run it on the host CPU. If you make certain changes to that code, then you can make that code run onto the IPU's hardware. So all those programs are here. So first, maybe we'll take a look at this matrix multiplication codelet.cpp code. So this is the code that will actually run on each of the tile inside a Graphcore. So you're basically creating like a vector for A and B for your dot product of a vertex, and you're calculating the partial sum and updating that to the variable. So this is what each of the codelet, each of the node in the graph is going to do, which they call vertex. Now, if you want to do this in a simulator, then you will be using this tutorial 5 complete.cpp program. And as explained in the slides, first you have to, like, this is most of the stuff is boilerplate code. So you'll be including a bunch of IPU model and tile mapping, various header files for that. And then this is a typical C program where you're basically checking if your result is correct. So you're doing this part of compute on the host and then checking if what accelerator has done is correct or not. Then maybe I'll start from the main part. So here, you're basically taking a command line argument, like how many number of rows and columns you want to decide like a size of matrix. Then you're creating this IPU model. So this is the part of the code that changes. If you want to run this code, instead of from simulator, if you want to do it on the actual hardware, this part will change. And I'll show that in the next thing. And then you're going to create a graph and then start adding your codelets. In our case, we just have one codelet there. And then you're going to create memory for that, create tensors, add variables, and then there will be part to like, so this is again all boilerplate code, creating a program and an engine, and the sequence, like in what sequence, like you're trying to give some control, like control flow to this data flow based program. So that's why you have to create sequence. So in which sequence first you want copy to happen, then you should do the compute and then the copy out. So all that part, and then you're running it and you're just checking the results. So that's how the host code looks like in C++. It's a different spin to what CUDA does, but the core ideas are same, like creating variables, copying them to accelerator, and then copying them back. And then IPU hardware complete. So this code is pretty much same as the code that I just showed you, except instead of creating the IPU model, you're going to create, like do this on actual device. So you're going to create this device manager, and then you're going to attach it to a particular IPU and run it on IPU. So that's how this code looks like. Then what you have here is, so what do you need to run this? So they have a compiler called as popc. So it's pretty much the way you use popc is quite similar to GCC. So first you have to compile your program, and once you have executable, you can run it. So if you want to run it on IPU, I have provided a makefile here. So makefile basically compiles the code. So if you want to compile it for the IPU, for the simulator, you'll be using this particular part of the makefile. So basically, you'll be using your GCC, the standard. You give your name of your host code in CPP, and then you're connecting, like attaching all these libraries like Poplar and poputils to that file, and then you're going to produce this output file. And then similar for this part is for running it on actual IPU. So this part will compile it for the IPU. So this is how the makefile looks like. So yeah, so you don't need, oh, this is still running. So yeah, we can try it here. So this particular example of GemV is taken from Graphcore tutorials. So I'll go inside this examples directory, then tutorials, and then Poplar, inside tutorials, Poplar. So yeah, here they have a bunch of tutorials where they introduce small concepts like variables, operations, vertices, profiling, etc. So we'll be using this matrix vector multiplication tutorial, and this number 6 is something that you can explore on your own, where they talk about some of the optimized ways to minimize the data transfers and improve the locality and how you can get better results. So that's in tutorial 6. But today we'll be looking at this tutorial 5. And inside that there's this complete directory. So this is what we are going to run. So let's first try running the IPU model. So for that, we just have to do make tut 5, and that will basically compile the program, and you should have executable called as this. And if you run it with, let's say, size of row and column 1000 by 100, then this is how you can run the simulator. So yeah, so it took very little time because it's small data set. And then similarly, you can also do this on IPU. So this is how you create that executable for IPU. But then there is little change. So in order to use the IPU, you have to actually get an IPU. So we'll be using this srun command from Slurm, asking it for one IPU and running the same executable. And then that executable had a command flag for device equal to IPU. So this is the command that is used to actually run that code onto the IPU. And now it will wait for resources, just one IPU, and then it will execute. So yeah, so So yeah, questions. Poplar is the name of software stack from Graphcore. Yes, now it's running on Graphcore. So are you referring to these things? Yes. Yeah, so this GC-Poplar is the name of the node that ALCF has given to the node, but Poplar is also Graphcore's software stack. Yes.
I saw a little bit different memory, more memory for thread, but the number of cores is not that different.
Yes. So the question is, what is the main difference between NVIDIA's GPUs and Graphcore's IPU? So one main difference is GPUs have a global memory. So whatever number of threads that NVIDIA GPUs have, they are looking at same piece of global memory. In case of A100, they are looking at 40 GBs of memory space. Yeah, so in NVIDIA's case, each thread can has idea about, like, for example, if you have a graph, then all of that graph is loaded onto the GPU, so all threads know what's going on there. In case of IPUs, each thread, first of all, is only getting executed on that small core, which has around 200 or 300 kilobytes of memory, and it can only access the memory in that part. So when it comes to porting, you have to parallelize your code in a very, very parallel way. So for example, if you have a graph, then you can only fit like a few nodes of a graph on one tile, and then you have to do compute related to that. The difference is all these cores are connected with very fast interconnect. So you have to think different way of doing computation. You cannot, for example, if you want to do gem, then you cannot fit entire row and column of a gem onto these chips. So you have to divide them into smaller blocks of rows and columns, compute the partial sum, send it to the nearby core. So there are different algorithms. So they work similar to tensor cores inside a GPU. Like if I have to give an analogy, it's not same, but you have to use different algorithms like Suma's algorithm or Cannon's algorithm to do matrix multiplication.
Are these still experimental? Would people actually use for real production tools, or are they still starting up? How much are they used in real life?
So these are still test beds, I would say, but the real production code can run on them. The advantage is you get much, much higher performance. So when you're doing your machine learning tasks on GPU versus IPUs or Cerebras, you see like 150 times speed up, for example, on Cerebras compared to the GPU, and at much lower power consumption. So we have some papers where we have compared the performance of HPC cores on IPUs versus GPUs. So we see like 20 times speed up, and then it takes like fraction of power on IPUs compared to GPUs. So there are those benefits. Yes. So one GPU, we were able to compare it with 4 IPUs. Both. So 4 IPUs because the system that we have, it has 64 IPUs that are distributed across 16 nodes. So that's what one rack consists of. So each node has 4 IPUs. So 4 IPUs are connected with super fast IPU links. So once you start scaling out of 4 IPUs, you start to see like performance issues. So we thought that's like a correct granularity to compare performance of 4 IPUs versus 1 GPU. And I'm pretty sure there are cost implications as well, but I'm not the correct person to comment about that. IPUs use very cheap very cheap DDR memory. So the memory structure that they have is like they have huge amount of SRAM, and then there is nothing in between. There is directly DRAM. GPUs are different. They have like cache and then the GPU memory, the HBM. So GPUs in general are much more expensive, but I don't know the exact numbers. Yes, so the question is like on CPUs, you have libraries like from Intel, you have MKL, for example, to do BLAS, to do GEM. So you just can call it GEM and then it will take care of efficient mapping. So GPUs obviously have similar libraries, like there is a CUDA BLAS, QBLAS. Similar to that, Graphcore has libraries, and that's what this part is about. So these are all the libraries here, like this pop-ops, pop-rand. So they for various utilities for linear algebra. So so the way I showed GemV, you don't have to really do it. You can simply call a GemV function. But because so there are two ways to do coding in Graphcore. Like you can create all these codelets, what exactly is happening on each tile, etc. So they call it vertex coding. Or if you don't want to do that, they have functions like, hey, like load my matrix A, like load like a row of matrix A, load column of matrix B, and then do gem operation. So they have these MKL-like functions as well. So you can directly use them, create a virtual graphs that will span across like 64 IPUs. So all of that is possible with Poplar, similar to MKL. Any more questions? You ask as many as you would like. I am happy to.
You just have access to the matrix vector products. So that means you have to solve some sort of a PDE on an input vector and you get a matrix vector product. And then we do some post-processing on the result of that. Now let's say we populate all these matrix vector products and then, okay, move it to the hardware and then do the post-processing. Like how? So is that like, data moving, is that a sort of a bottleneck?
So it depends on the size of the data. So
Let's say it fits the size of the memory. It's not, I mean, in one go, it's not that bad. So in that case.
So if you're going to move data onto the chip, it's not a bottleneck. Okay. If you want to move data off the chip to the on the chip, then that's probably going to be a bottleneck. Based on my experience, the main problem was to restructure your program, make it parallel enough so that you can fit it on a tile. Like we worked on a simple problem of calculating number of triangles in a graph. So on a GPU, you just have like a 5,000 node graph in the global memory. You don't have to worry about it. You just write your logic and you're done. But here you have to think about how would you distribute them across like 1,500 tiles, and how each tile will have access to its own data of a graph, and then how those tiles should communicate. So you have to think about a problem in BSP way. So if you have a problem, whatever you're discussing, you can Google how BSP algorithm for that. And there will be some algorithm that used to work on some old supercomputer. So if you can port that algorithm here onto the chip, you'll see like huge benefits. So that's the way to approach Graphcore. That's only applicable to Graphcore. You want to do it on Cerebras, you have to, okay. Some parts are same, but many others are not.
Thanks.
Yes. Yes, you can say that. Yes, everything has to be done manually here, but you probably will have to, like, there are some libraries there which allow you to automate that task of tiling, but if you want to do it manually, you can do it. The best way to go about it is look at the example codes, see how they have done it, and go about that. One good resource that I'll add later on is from Graphcore itself. I think it's called Graphcore Research. So that's a very good place to take a look at how they have doing things, like how they are using Poplar to port most of the simple things. So this is a very good repository. I'll add it to the resources here. Okay, so any more questions on Cerebras or Graphcore? Yeah, but before starting with the next topics, any questions? Were you guys able to run?
Any of the AI testbed is or are running production?
Yes, all the AI test beds, all 4 of them are production. You can get access to them. You can port and run your codes. The list of papers that I showed earlier, like we use this test beds to produce results better than GPU. So yeah, they're very good. Yeah. So should I wait or can I get started? What's the call? I can get started? Okay. Okay, so if there are no more questions, we can start with the next topics. So the next is the introduction to the third test bed that we have here. So this one is from SambaNova. It's called, so the version that we have is SN30. So this is a picture of a chip, how it looks like. And then, so one difference here is like this chip consists of, in addition to like how many flops and everything, it consists of something called as PMUs and PCUs, as you'll see it in the next slide. So that's how they divide the memory and compute onto the chip. Each chip has 640 MBs of on-chip memory. And in addition to that, the novelty about this chip is, in addition to SRAM, it also has multiple layers of memory hierarchy. Like it has SRAM and then HBM and then a lot of DDR memory. So if you're not able to fit something onto the chip, there is a way to offload it to these other tiers of memory. Again, you don't have to do that manually. Compiler takes care of that. As I was just explaining, so inside each chip, it's divided into 8 tiles, as you can see in this figure. And each of this tile consists of like a fast interconnect. And the smallest unit here is a PCU and a PMU. So PCU stands for pattern memory unit, and PCU stands for pattern compute unit. So compared to the other 2 test beds that we discussed, each core doesn't have a compute and a memory. Like compute and memory is distinctively differently laid out on this chip. So those are the novel parts about this chip. So similar to Cerebras, SambaNova is also a data flow based architecture. And these are some of the slides in context of machine learning, how different layers, for example, here you have various convolution and pooling layers, how they get mapped onto the chip, onto this set of PMUs and PCUs. So they get mapped based on the amount of memory required for each layer onto various parts of a chip. So you can think of it as like a pipeline parallelism way of executing the data and laying it out in a spatial way. So this is how, again, like if you have a particular machine learning model, this is how it will get mapped onto the chip. Compiler will do a job of this. You don't have to do this manually. So what do we have at ALCF? So in ALCF in production, we have this SambaNova data scale solution. So it has 8 nodes, a total of 8 terabytes of memory, and each of these chip consists of 8 tiles. So that's how the system looks like. So total we have 64 of RDUs at ALCF. Now speaking of software stack, so they have it's called as Samba Flow. So at the top level, like you're again going to work in PyTorch. You're going to take the models that you have in PyTorch and you're going to map them onto the underlying architecture. So these are all various parts of the compiler. The executable, like something equivalent to executable that you have on a CPU that you have here, it's called as a PEF. So there are 2 stages. First stage is compilation and the second stage is execution. So the output of the compilation stage is this PEF file, and then you take that PEF file and then use that to run it onto the underlying RDUs. So that's how the software stack looks like. So yeah, that was brief about the software stack, and then we can get into the hands-on part. So back to the same directory, we'll be going into this SambaNova directory here. So similar to the Graphcore, from your local machine, you have to SSH to sambanova.alcf.enl.gov, which is the login node. And from there, you have to SSH to one of these nodes. You can choose anything on random. And once you're on that node, you get access to like scheduler and all the RDUs in the system. SambaNova doesn't have like a model zoo or anything, but they do have set of applications. These applications are present on the system itself under /opt Samba Flow apps. So yeah, we can do these steps to begin before moving to the next steps. So first SSH to this. So with your username, you're going to SSH to this. And I already have a concurrent session running, so it didn't ask me for a password. But once you're on a login node, you have to connect to one of the nodes. I'll just choose the first one here. Yeah, and we are here. So let's take a look at this. Now that my VS Code is working, we can take a look at what this application or this apps directory consists of. So it's in my apps. Okay, so this directory here that I have copied in my home directory consists of various apps. If it opens, so every demo has certain parts that fail. So my demo has VS Code not working for me. So VS Code is running on my local machine, but VS Code has this extension which allows you to connect to remote machines through SSH. So that's what I'm using. So there is a VS Code server running on the login node of all these AI Testbeds, similar to how VS Code will run with Polaris, for example. There is an extension in VS Code which allows you. It's called remote something. I mean, you just have to go to extensions and just type SSH, I guess, and install like remote SSH one from the Microsoft. But yeah, it's somehow not working for me. It worked. Okay, so this is how the on the left-hand side sidebar here, these are all the contents of the apps directory. So this is local on your machine. I have copied it to my home directory. So it consists of various applications from NLP to like a starter programs to understand like MNIST. So this is the structure of it, of this apps directory. So yeah, you just copy this app directory to your home directory. Don't directly work. I don't think you have access, like write permissions to write here either. So make a copy in your home directory. Now for the SambaNova, you don't have to create separate virtual environments manually. What they have done here is inside their apps directory itself, for each of the application, they have virtual environment. For example, for MNIST, so they have created this virtual environment. So each app directory will have a pre-built virtual environment. So you just have to go and activate that virtual environment. So they have, if your application is one of the applications that you're trying to run from this directory, you don't have to create a new virtual environment. You can just use the one that already exists there. Just activate it. And it will have all the dependencies and everything that you need already available there. Then similar to other testbeds, there are some paths that are available for your convenience, and I have just noted them here. So one of them is, which I already showed you, is this Samba Flow Apps directory, which I'm showing. Other than that, there are some scripts that are useful. You can also, one second. Yeah, so this script directory has a lot of pre-built scripts there, so maybe I can show them here. So yeah, there are lots of science applications that Argon is working with SambaNova. So there are some ready-made shell scripts which will take care of compiling as well as running the particular application. So all those scripts are available here. So if you are curious about what all steps are involved in running something, the script directories is something you should take a look at. And then similar to others, like the commonly required data sets that are needed for SambaNova system. So all of those are present here in this datasets directory. So you don't have to re-download them and reprocess them like Open Web Text or Wikidataset, etc. So it's all available here. So yeah, that's all about the preliminary stuff. So the example that we'll be going with hands-on today, similar to the other two platforms, is the GPT example. For this example, we are going to follow a little different path than actually digging into the example, because we have the scripts ready. So what you have to do is create this directory called as GPT 1.5 billion single on your home directory. And the scripts to run the GPT 1.5 billion parameter training model to compile and run are present inside this scripts directory on the system. So for the sake of this hands-on, you can just invoke that .sh file and it will compile and run it. Yeah, that's all you have to do. So let's open this and we can go through the scripts, what they have. So I have already copied these two relevant scripts into my VS Code. So this is how a script to compile compilation for GPT 1.5 billion parameter model looks like. So I would not go through. Yeah, I would not go through all of the, like we are basically setting number of OMP threads and all this boilerplate code. But I want to point you to the, and I'll also, yeah, I'll point you to this part of the command, the exact command that we'll be using to run this. So the command that we are going to run is basically to compile is Python, and we are going to use from apps NLP transformers on RDU. So this is the Python script that we are going to use. We are going to compile, and it's going to create a PEF file that, as I mentioned earlier, it's something similar to executable file. And then these are all various command line arguments that that you're going to give, like what should be the output directory, batch size, sequence length, etc. for the training. And once that's done, the script will automatically also run this code. So for that, we'll be using sbatch, and we'll be pointing it to the PEF file that we just created. And there is a separate script for that, which is this script, run.script. So this is where we'll be giving name of a PEF file that we just created in the compile step, and it will run this code. So yeah, pretty much everything is like kind of inbuilt in these two scripts, and one script is basically calling the other script. So all you have to do for this hands-on is just call one of the scripts as I have mentioned here. So you just have to enable, like, make sure that it's executable, and then just run it. So we'll go to this directory, and make sure that it's executable, and then you can simply run it. Yeah. So that's pretty much all. Now, if you want to check the status of what you have submitted, you can use Slurm here again. So you can use SQ, and it's not submitted. Okay, so you have to check here for the output, because that's where we are writing it. So it's not able to run. Open this. So this does exist. So probably permissions issue. So it's just underscore run. So that's 1.5. Okay, so at least we can compile it. So it worked for me. So we can comment out this. See if this works. Looks like some issue with this. Yeah, so it's compiling. So there's some issue with the run script, which is not there. So maybe we can use this script. Yeah. Yes. Learn.sh. Is this? Okay. Okay, so for some reason this is not working, so I would not spend more time on debugging it, but we can try some other example here. Let's say we can go to these examples and maybe we can try something simple like mnest or lenet to show you, like, yeah, we can try this lenet scripts. So yeah, let's try to follow this. So yeah, we have to go to the correct directory for where lenet is present. And as I mentioned earlier, for each of the applications, there is a virtual environment, so you just have to activate that. Okay, so we have that particular virtual environment activated, and then you have to, there are two steps, as I said, there is a compile step and then there is a running step. So we'll first compile this example using this command. So this should be creating a PEF file called as lenet. And the next step is to point this script to this PEF file and run it. Yeah. Yeah, so the compilation on most of the AI accelerators take longer time than what we are used to on GPUs and CPUs. Yeah, so while that's running, we can check the status of the other jobs that we had on Cerebras. So I believe this job is still running and this still don't have resources. Okay. Okay, so we are done creating the PEF file, the compilation process. It's saved in this location, and then you just have to point this Python script to that location and it will run on the RDO. Yeah, so it's starting to run and it will go up to 60,000 images and it will finish. So the steps are pretty much same for GPT model as well. There is a compilation and run, which we tried to abstract in this simple to run scripts. So you should be able to run those examples as well. Once I'm done with this talk, I'll fix the scripts. But basically, that script to run it is not available there, so we'll look into that. Okay, so that's all I had for the hands-on part for the SambaNova. Any questions about all this workflow or anything you guys want me to dig into? Or any questions about the 3 test beds that we discussed?
In general, how do we check allocations and disk space and that sort of things?
So for the allocations, So it's the ALCF accounts page. That's what, like the same page that you use to check your allocations for Polaris. So you go and check there if you have access to the systems, or so that process is same.
It doesn't show current allocation. I mean, how many hours
I am not sure about that part because I don't use that. Maybe someone here can use, like, how to check. Yeah, like how do I check how much allocations I have on the system?
I don't believe SBank is installed on the AI Testbed
It
system.
varies from system to system.
But I can take a quick look, but yeah, it does, yeah. So they're not traditional allocations the way we have them on the other systems. So that's why you probably won't get an email saying your allocation is expiring. You won't see that for the AI Testbed. So once we set it up, it's kind of enabled and you can just submit jobs. That's right. Yes, yes. So the start and end date of an allocation tells you whether you can submit jobs, but the balance doesn't really matter on the AI testbed systems, unlike the other machines where, your balance tells you how many hours you have to burn through. So there's a slight, I wouldn't say infinite, but yeah, there's no concept of the traditional node hours on these machines.
Yeah, once the allocation for the workshop is done, you can try the director's discretionary allocation to try running your applications there. So I think the reason is there are not that many users, and like we are trying to work with users to get more users on board these. That's why there are no allocations. So I don't know what's the upper limit for that, but your home directories have some limit, like 40 or 50 GBs. But other than that, the file systems that are accessible on Polaris and Sophia are not available here, like Grand and Eagle. They have some different file system, and like that space is quite huge as well, like terabytes of space. But that share across your work group. But again, I don't know what's the upper limit on that. Okay. Yes. So what I have in my home directory currently, it's mix of everything. Like there is Cerebras here, and there are Graphcore examples. There is SambaNova, everything. And in addition to home directory, I also get this projects directory. So they have all these projects here. So this is where you get like the real disk space, like through all these projects. So that's where I have, like in data science is where I have my projects directory, which I typically use. Any more questions related to architecture or how to run things on SambaNova? So, so Cerebras and Graphcore had HPC software stacks that we walked through. So SambaNova doesn't have one yet. So that's something I hear that they're working on, but currently there's nothing to discuss yet. So that's another difference between, like, if you want to do GemV or any FFTs or any traditional HPC applications, that's currently not possible on SambaNova. It's in theory possible with all the compiler stack and everything, but they don't have anything public facing yet. Okay, so Any more questions? If not, we can start with the next and the final test bed for today. So how do you run your model? So it again uses a PyTorch. So I can walk you through. So it's similar. Like, so first you compile. So you take your PyTorch model and then you compile it. You create a PEF and then you execute it. So you. So there are differences. For example, we can walk through the simplest Linux code here, right? So here, like for CUDA version, you have to depend on CUDA specific imports. So here you have to import all these Samba flow specific libraries in this Linux code, and then creating the model part is pretty much same. The forward pass and everything, and this is just typical Python command line arguments. But yeah, where you run it is different. So they have their custom data loaders that make sure that you're loading your data onto the RDUs. So you have to use torchvision.datasets here, for example. So those part will be different than the CUDA implementation. So you have to use custom data loaders, and then so these things basically, if you can go through the code and search for torch vision and transformers, so these will be different. So this is not the typical transformers that you use from pip install. This is the one from the torch vision. So those are the differences. Yeah. So all these files with torch vision, those are the files that you have to change in order to get your own model running on the SambaNova. This is the simplest example. Did that help you to answer your question? Okay. Yeah, I mean, you do face issues like certain operations are not supported and you have to write custom kernels for that. And so, but if everything is supported, this is the typical workflow. Okay, so since no more questions, we can move on to the final test bed. So this one is from Groq. They changed the name of their processor. Now it's called LPU. It's called Language Processing Units. After the ChatGPT, I think before that the same chip was called TPU, Tensor Processing Unit or something. So, but the architecture is same. So for this chip of Groq, it consists of 230 MBs of memory. So it's the smallest amount of SRAM of all the AI accelerators that you have. Then on chip, the compute units are not generic, like it doesn't have like a processing element. It's divided into matrix vector multiplication unit and matrix multiplication unit. So I'll show that in the next steps. Then all these LPUs are connected with super fast interconnect as well, and they claim, and like their idea is to keep everything inside on the chip and across the network in a consistent way, like in a coherent way. So that's where the Groq has the advantage. So as I was explaining earlier, like chip consists of these building blocks like matrix vector multiplication, vector operations, reshaping operations, and some amount of SRAM. And then all of these are on the chip. So the chip consists of these blocks with some memory, and then these compute units. So yeah, one of the thing about this architecture is it's a flat memory architecture. So there is no L1, L2, L3 cache. Everything is deterministic inside the chip, and when you're moving across the network, then also it's deterministic. So this architecture is very good for low latency if you're able to fit your models onto the architecture. One other difference between Groq and other accelerators is Groq is only targeting this architecture for inference only. So you cannot train your models onto the Groq. But if you have a model trained, then you can get it onto the Groq and then get a very good results for inference. How to do that, I'll talk in the next slides. So at the heart here is the Groq chip, the LPU, and then they have these various products like Groq card. So what we have here at LCF is one Groq rack. So it consists of eight of these Groq nodes. That's what we have access to here. Then speaking about the, yes. So Google's, it's a different architecture. So the TPUs that Google has and LPU is not same. The same people who used to work on TPUs, they started their own company and they are at Groq now. So the architecture is quite similar. Yeah, they used to be at Google, but not anymore. So if you look at the architecture, like the name of the chip itself, it's same, but there are fundamental differences there. TPU mostly has these systolic arrays, and that's the main part in the TPU. LPUs are a little different.
Looking at an ALCF video, it says ALCF AI Testbed, the training, large language model with Groq. So it looks like somebody did training.
Yes. So there are lots of, for all the AI accelerators in last 2-3 years, there are a lot of training activities that keep happening. So the one you're looking at, I don't know which one it is, but the last one that happened was back in the summer, and all those videos from those activities are posted on YouTube. That particular activity was probably in collaboration with Groq. So some people from vendors come here and then they present this information. So yeah, that's the next training activity will be in supercomputing. So we have a tutorial there. So we'll be talking about this stuff, like how to get your things running on ALCF systems, as well as all these vendors have their clouds. So you will see how to run inference on like Cerebras cloud or SambaNova cloud, etc. So and then additional applications like RAG and function calling, etc. So there are lots of other training activities targeting AI accelerators.
Just a little question, because you said that you don't train on Groq, you only do inference.
Oh, so I think that training means they are teaching you how to use Groq, but there is no inference on Groq. Okay, that's what you meant to say. Okay.
So you cannot train a model on Groq.
With their current software stack that ALCF has access to, no. There were talks of extending that to training, but I don't know when that's going to come out. So currently you can't do training. Yeah, and that's what this software stack also talks about. So they do have support for PyTorch and TensorFlow, but once you have your models trained there and you have your model there, you have to export those to Onyx. That's what this layer is about. And then that Onyx model is what you map onto the Groq architecture, and then you run inference. So it's inference optimized, and currently they are only targeting the inference market for now. Yeah, so that's what the software stack for Groq looks like. For machine learning purposes, you just have to worry about the topmost layer, PyTorch layer, and they have this function called as Groqit, which takes your PyTorch model and converts it into Onyx and runs. There is another entry point into the software stack from the compiler point of view. So if you have some other non-ML workloads, then there is a way to use Groq compiler and execute those programs onto the chip as well. So yeah, like typical development flow on Groq looks like you have to modify your PyTorch model, export it to Onyx, and then Groq only supports FP16. So you have to convert your model from FP16 to FP32 to FP16, and then you have to compile it, and then that executable gets mapped to a single Groq chip or a Groq node. So all of that mapping of model to multiple chips is taken care by the Groq compiler. So that's how simple the flow looks like. So yeah, that's what I had for the overview part of the Groq. Now we can get into the hands-on part. So again, in the same directory, you have to go into the Groq directory. So the first step is to connect from your local machine to one of the login nodes for Groq. And once you're on the login node, you have to connect to one of the Groq rack nodes here, similar to other two systems like SambaNova and Graphcore. Once you're there, you have to create a virtual environment, which is the step is quite similar to the other test beds, but here it's a little different. So here you are going to use Conda, like mini Conda, to create the virtual environments instead of relying on Python's inbuilt virtual environments. So that's what this step is about. You have to download Miniconda to your home directory and then install Miniconda. And once it's installed, you have to create a new PyTorch virtual environment with this particular version of Python, because with the latest Groqflow software release, that's what they support. And that's where the Groqflow comes into the picture. So Groqflow is available on Groq's GitHub page. So this is how that repository looks like. It consists of the Groqflow, which will be installing virtual environment from, and all the examples you'll see in this proof points directory. They don't have many examples like others, but for NLP, they have this mini LM, which is like a mini version of, it's a mini LLM basically that can be fit on the rack that we have here. In addition to that, they also have like BERT and Roberta, like these other examples here. So you can try out all these examples. So yeah, this is about the Groqflow. So yeah, once you have created a new virtual environment, the next steps are to clone this Groqflow and then installing the Groqflow. So let's do that. Okay, so let's SSH to Groq. Again, enter your password. Okay, so now we are on a login node. So from login node, you have to connect to either of these nodes from 1 to 9. So I will connect to the first one. Okay, so this is where you're going to create your, like download your Miniconda. So I already have this downloaded, so I will not download it again. It's already present here. And similarly, I have also installed it. So I will not install it. But what's missing is it's not initialized. So I will just call this bash rc so that it will initialize my Conda. So now that I have access to Conda. So this is where you should be. So in my Conda, I already have an environment called as Groqflow, but let's create a new one. So for that, first I'll export the version of Python, and I'll create a new environment called as Groqflow. I'll call it Workshop, but you can name it whatever. Yeah. And once the environment is created, you can just activate it. Okay, so it's created new environment, so I'll just activate this. So the next step is to install Groq flow. So first you have to clone the repo, and I believe I have the repo, so create a workshop. Okay, so I'll just clone here, Groq flow, and then get into that directory, and then just first upgrade the pip, and then just install it. So these are all the files here. So it will be using this setup.py, and you can just install the Groq flow. Now, in addition to that, they also have some demo helper scripts that you have to install. So we can do that. Due to OS error. Has this changed? Okay, so these are the more updated. Okay, so we can follow these. Okay, so while that's going on, I can explain the next steps. So for job queuing, we are again using the normal commands that you're used to from the previous job scheduler. So you can use queue sub to submit a job, check the information of the queue, delete the job, and put it on hold, etc. So there are two ways to submit a job on using this. So one is your batch job, and other one is the interactive job. Interactive job is quite easy. You just say queue sub, and this is for interactive, and give the amount of wall time you need, and you can also give like how many number of CPUs you need and how many accelerators you need, etc. So that's how you do the interactive job. Doing a job script is a little difficult. So because you have to depend on the conda, so basically for your job script, you just have to add this conda initialize in your submission script, and then activate the correct conda environment, and then go to the directory, install the requirements, and run the job. So that's how a typical submission script looks like for this accelerator. Okay, this is still going on. Yeah, so there are several examples for this in this repository. Today we'll be going through this GPT-2 example, following similar to the other accelerators. In addition to that, they also have this mini-LM and ResNet 50 example. In addition to that, in proof points directory, there are many other examples that you can try. So yeah. Okay, so this is done. So we'll go to the next step here. We'll install the demo helpers. This should be quick. Okay, and the last requirement here. Okay, yeah, so with that, now we are ready to run our example. Before we do that, I'll just get a node interactively here. And then we can get into the GPT-2 example. So yeah, so as the instructions say, we first got the node interactively. You can again submit this as a batch job. But okay, so we got the interactive node. And the example for GPT-2 is actually not present in the proof point. So we have to rely on the GPT-2 example, which is present here. So for that, you can git clone this repository and then go to the correct directory. So let's do that. Why not? Oh, it's already there. Okay, so we are here. So since we are on an interactive node, we have to again activate the Conda environment. And because there is Conda, I will do this. Okay, so this is the Groq flow workshop. That's the latest environment that we created. So we'll activate that. And with that, we are ready to run the example. This GPT-2 dot. Yeah. So the code for this looks quite easy. Like maybe I will run this first and then we can go through the code. There is a requirement for transformers, but I believe that should be already installed here. Yeah, there is a version of transformers there, so we don't have to install that. So now we can just run this python to gpt.py, and this will take some time to run. Okay, so I have faced this issue before. So sometimes there are issues. So you just have to reset the system for that. And then you can run it again. Yeah, so while it's running, we can go through the code, which is quite easy as well. So all we are doing basically is we are importing Groq from Groqflow and the model that we want from GPT-2, and then basically we are providing that model to Groq function here, which is converting it into Onyx model and then running it for inference. So that's how this code looks like. It's quite easy. And yeah, for this particular code, the inputs are going to be synthetic inputs here. So that's what we are doing. And this is like some synthetic output that it produced as an inference stage. So yeah, that's how you run the GPT code. So for me, because I have already done this before, what happened was like this model, like the compilation was already cached, so it directly used it from my cache. But for you, this step will take probably more time to convert model to Onyx and then actually run it. So be mindful of that. I guess that's all, unless you want to run more examples or something, like we can go through mini-LM or ResNet, we can run those examples, but that's all I had for the hands-on session for this Groq. Any questions? Yeah. So I'm not aware of like if Groq, so they probably have like, so the limitation with Groq is like, because each Groq chip only has like 200 MBs of memory. One Groq rack has like 8 of the nodes. So how big of a models you can fit on like a rack is quite limited. So um, so so probably if you have a Groq system which is big enough with like 500 nodes or something, there you can run MLPerf benchmarks, and that's what you would probably see there. So it's certainly possible, but that's not something I have ran personally. So yeah, if you have a big enough system, then you can certainly run those things. Um, what you can run on the system that Argon has, it's like models up to like maybe 7 billion parameters, not larger than that. But yeah, it's possible.
How is it possible that Groq can only run inference but not training? Is this a hardware, software issue that stops it?
I don't believe so. It's a business decision that they made. They had, I guess, they had limited engineering available, and they decided to focus on inference market first.
If I have to train a model with Groq, is it possible?
With today's software stack, it's not possible. Perhaps there will be a software stack next year or something. Right. There was discussion about having that, but then these are all startups, so it's quite volatile area. So currently you cannot do training. So the advantage is their inference numbers are fastest. They are hundreds and 200, 300 times faster than GPUs. They are way faster than any other AI accelerator as well. So if you go to Groq's website, like they will claim they are fastest among everything, and the latency is a other advantage. So if you have a big enough Groq system, then you will get the maximum number of tokens per second, for example, compared to any other AI accelerator. And the latency will be least of them all, because it's all working under like a deterministic system, even if when you're going off chip. So that allows them to do kind of optimizations that are not possible on GPUs or any other AI accelerators. So that deterministic execution is what they depend on. So that makes them the fastest for inference, and probably at a lower cost, but we don't have numbers to justify that. Yeah, we can quickly check what's going on Cerebras. The training job that we submitted is running. The other one is still waiting. Sorry? On the Slack? Is the tutorial on Slack? What? So there is a Slack channel for that. You can ask questions there. For the tutorial, we have a GitHub page. So this ALCF Hands-on Workshop, AI Testbeds directory has all the material there. The slides for this tutorial, I have already uploaded them on the Slack, and I'll also upload them in this GitHub after the talk. Yeah, yeah, that's all. So feel free to ask more questions. We can keep talking about any of the AI accelerator or why we need them, challenges, whatever. But yeah, like this material, like all these people helped me, like Murli, Varuni, and some of the, like Krishna and Venkat were here, and most of the material is used from the other training sessions from various vendors, etc. So thanks to all of them. And if you have any more questions, feel free to reach out on Slack or email. And yeah, I'm here if you want to discuss anything.
Wow, thanks a lot, Sid. Let's thank him. That was a lot of material for him to cover. Yeah, so yeah, are there any additional questions on the topic of AI test beds?
Yes.
In terms of performance, actually, how is Testbeds compared to NVIDIA-based?
So generally speaking, they are better. If you want the exact numbers, I would forward you to these papers that we have. So there are lots of papers there which are comparing the performance. For example, the latest paper is comparing the performance for LLM inference. So how the numbers look like across various AI accelerators with various GPUs. Before that, and that is only focusing on inference. So you can go take a look at that paper. I can show you some of the graphs from that paper. Before that, we targeted this paper for pre-training, so how the performance looks for GPT-2 model. Before that, we had papers for comparing performance across AI accelerators for various CNN models. So there is work like that. One of the work that Krishna shared, maybe I can do some marketing. So LLM inference. So this paper, right? So we have a dashboard for this paper. Here you can choose which accelerators you want, right? Like let's say you want to see how much is the power consumption or how much is the throughput. For example, you want to see it for like you want to see how NVIDIA A100 compares with SambaNova, for example, and for 1 or maybe 8 accelerators, and for which VLLM framework, for which model, you can choose all that and then generate a graph for that. I probably missed something. So yeah, you can use this dashboard to see the performance for inference, or you can visit the other papers that we have to see how the performance compares. In general, they are better on both sides. How much better, which one is the best, each one has some advantages compared to other. So those exact numbers, like it's an in-depth performance comparison. That depends, but in general, they are better than GPUs. Yes, they are better than GPUs, but then there are porting challenges, right? Like there are some pros and some cons. Like the model that you have on GPU, it takes some efforts to port it to any of the test bed. So there are those challenges as well.
Yeah, one of the things we're definitely interested in hearing from all of you is your experiences with the AI test beds, and what do you like about them? What don't you like about them? What do you think about SambaNova compared to Groq, and these kind of things. So if you could provide feedback on that for us, that'd be great as well. Is there any more questions? All right, let's thank Sid again.
Okay, thank you.